Hello everyone. My name is Dr. Aradhna Sahu, Associate Professor, Computer Science and Engineering Department from Shri Santosh Rungta Group of Institution, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. Welcome to video lecture on applying wavelet based image compression using Python programming. In previous lecture, we have discussed the basic and fundamental concept of wavelet image compression technique that uses wavelet transform to compress images. Wavelet transform is a mathematical transform that can represent an image in terms of frequency component, allowing the efficient compression while preserving the image quality. In this guide, I will provide a introduction to wavelet image compression and outline a Python programming using popular libraries like PyWavelets. Before start the lecture, let us revise the basic steps involved in wavelet based image compression. The figure 1 depicts the step-by-step method for image compression transformation using wavelet algorithm. The first step in that the original image is embedded into the system. Then the system will transform image into grayscale to minimize the storage size in the disk. The grayscale image is gone to wavelet transformation, either first, second and third level of decomposition. The process of these transformation is to separate information into subsignals. Then the system is quantized the image. The result is wavelet compression image, where the compressed image size is reduced, but the quality of image is quite similar to the original image. The step we should follow for performing wavelet analysis. So here are the basic overview how to perform wavelet analysis using the Python. For this, we will start from importing the necessary library files. Begin. Important the necessary Python libraries such as PyWt or SkyPy are used. Then second, data preparation. Prepare your data, which could be a time series, a image or any other signals. Then selecting a particular wavelet to choose appropriate wavelet function based on characteristics of your data and analysis the goals. Now the common choices include are Haar and Morlet waves. Then decomposition process. It applies the wavelet transform to your data using functions like pywt.wavedeck methods or skypy.signal.cwt. These steps decomposes your data into the approximation and detail coefficients at different scales or levels. The thresholding, it is optional. In some applications, you might apply threshold to remove small coefficients, effectively denoising the data. Then reconstruction of image if needed. The reconstruction the data from wavelet coefficient using functions like pywt.wave rec method or by performing the inverse transformation. Then visualization. In this process, the wavelet decomposition and reconstructed data using Python library like matplotlib to gain insights into your data's frequency domains. So let's get started the wavelet transformation using Python programming. We are using PyWavelets library to implement the wavelet transformation. The PyWavelets is a Python wavelet transform module that includes ND, forward and inverse discrete wavelet transform, DWT and IWT 1D and 2D forward and inverse stationary wavelet transform, undecimated wavelet transform, 1D and 2D wavelet packet decomposition and reconstruction. Let's understand in a simple way of how you can perform a wavelet transformation on an images. So, we will go through the steps. The step 1 is install Pi wavelets. If you have not already installed Pi wavelet, you can do using pip. Type pip install Pi wavelets. It is commonly abbreviated as PyWT library to perform a 2D discrete wavelet transform. The operations on an input signal or image representation by the original signal. Then next, we have to import all the library files. Let's write and understand one by one. For this, we type import pywt. This is the Python module for Wavelet library. The PyWavelet is a library that provides tools for DWT and IDWT operations. It allows you to analyze signals and images in terms of their frequency components. Then we need to import pywt.data. This is the name of a specific module or a sub-package within the pywt package. After importing pywt.data, you can use the function classes variable defined in this module to work with wavelet transform related data, constants or utility functions. Then we import numpy as np. It is numpy with the alias np. You can use numpy's function and classes by prefixing them with np. It provides supports for arrays, including multi-dimension arrays, mathematical functions, and tools for working with data. Then import matplotlib.pyplot as plt. It is a commonly used import statement in Python for working with the matplotlib library. It allows you to import the pyplot module from matplotlib and give it an alias of plt for convenience when using these functions and classes. Then import CV2. The OpenCV, Open Source Computer Vision library, is a popular library for computer vision tasks, image processing and video analysis. The step 3 is create or load your image. We can type original equal to pywt.data.camera. These lines of code appears to be using the camera function from pywt.data module, which is part of PyWavelet's library. This code is typically used to load a sample image known as the camera image provided by PyWavelets for testing and demonstration purpose. Or if we want to load image from file, for this we have to write original equal to cv2.imread, and it takes one parameter image underscore path. Here this parameter can have the path of our test file. In order to compress the image, the wavelet analysis can be used to divide the information of an image into approximation and the details subsignals. The approximation subsignals shows the general trend of pixel values, and 3 details subsignals shows the horizontal, vertical and diagonal details or changes in the images. So, we make a list that maintains the information about wavelet transform of image and plot approximation and details. So type the name of list like titles equal to maintaining the list here, approximation, second is horizontal detail, vertical details and diagonal details. In the next step, we will code for wavelet transformation. For this, we can type coefficient 2 equal to pi wt dot dwt2. It will take two parameter, original and BIOR 1.3. This line of code performs a 2D discrete wavelet transform DWT using BIOR 1.3 wavelet filter on the input signal or image represented by the variable original. This operation decomposes the input data into different frequency subbands, allowing the various types of signal analysis and processing in this line. The DWT2 function is a function provided by Pi Wavelets library that performs a 2D discrete wavelet transform DWT on an input signal or image. The DWT2 function is used for 2D data such as images to decompose an image into different frequency subbands. Original is the first parameter. Actually, this is the image on which 2D DCT will be performed. The DWT decomposition these input signal or image into multiple frequency subbands, capturing the both high frequency and low frequency component. In this method, BIOR 1.3 is the second argument specifying the type of wavelets filter to be used for DWT. In this case, it specifies that BIOR 1.3 wavelet, which is a specific type of biorthogonal wavelet filter. Wavelet filters are mathematical functions used for analyze and transform data in the wavelet domains. The different types of wavelet filters have different properties and are suited for different types of signal processing tasks. The next step is decomposition of coefficient. Wavelet transformation is a mathematical technique used in signal and image processing for analyzing and decomposing the signals or images into the different frequency components. The transformation breaks down the input into the set of wavelets coefficient which generates the data in both time and frequency domain. The one way to represent the coefficient is through 2D decomposition, where the data is split into four sub-bands. They are LL means low, LH means low-high, HL means high-low and HH means high-high. This decomposition is often referred to as coefficient 2 in our code. So, for this type LL, LH, HL, HH equal to coefficient 2. Let us understand it. Brief explanation of these. The LL, low. These subbands contains low frequency information in the both horizontal and the vertical direction. It represents the core set scale or approximation of the original signal or image. The LL coefficient capture the low frequency components and provide a low resolution representation of the input. Next, LH means low-high. The LH sub-bands contains low frequency information in the horizontal direction but high frequency information in the vertical direction. These sub-band captures details that vary vertically in the signal or image while smoothing our variations horizontally. The HL high-low. The HL subbands contains high frequency information in the horizontal direction and low frequency information in the vertical direction. It captures the detail that vary horizontally while smoothing our vertical variations. The HH means high subbands contains high frequency information in the both horizontal and vertical directions. It represents the finest scale detail in the input signal or images. So HH coefficients capture high frequency component and provide the high resolution representation of local variations. So the wavelet transformations such as one and mentioned with the coefficient 2 are often used for various applications including image compression, denoising, feature extraction, and data analysis. By decomposing the data into these subbands, it becomes possible to analyze and manipulate specific frequency components to achieve various signals and image processing goals. The next line of the code is figure FIG equal to PLT dot figure size 12,3. The PLT is an alias name of matplotlib as we have already discussed, and it calls the figure method using plt.figure. The figure size parameter specifies the width and height of the figure in inches. Here the figure will be 12 inches wide and 3 inches tall. So you can then use fig object to add plots, axes and other elements to your figure. In the next, we will create for the loop to create a figure with the respect of 4 subplots, each displaying an image represented by the variables LL, LH, HL and HH. These images are typically associated with some kind of image processing or signal processing, such as a multi-resolution decomposition using a wavelet transform. The code uses the matplotlib library in Python for visualization. The code of the for loop is shown in figure 2. The provided code is used. Let's a breakdown of each step part of the code does. The line 1 of the code is for I, A in enumerate LL, LH, HL, HH. This line sets up a loop that iterate over the elements LL, LH, HL, HH while keeping the track of loop index I and the current element as A. These elements are assumed to be images or array that will be displayed in the subplots. Then type AX equal to FIG dot add underscore subplot and 1, 4, I plus 1. Inside the loop, this line adds a subplot to the figure. The add subplot method is used to create a subplot grids with 1 row and 4 columns, 1, 4. The I plus 1 argument specifies the position of the current subplot within the grid, which increments each iteration, and these effectively arrange the subplots from left to right. Then type ax.iamShow interpolation equal to nearest, and the third parameter is cmap equal to plt.cm.gray. So this line displays the image A in the current subplot AX. The IamShow method is used for showing the image. The interpolation equal to nearest specifies that the image should be displayed without interpolation, that is pixeled, and cmap equal to plt.cm.gray specifies that a gray scale color map should be used for displaying the image. The type ax.set underscore title, tiles of 1, comma, font size equal to 10. This line sets a title for the current subplot based on the titles list at index I. The titles list is assumed to contain titles for each of the 4 subplots. Then ax.set underscore x ticks and ax.set underscore y ticks. These lines removes the tick mark on the x-axis and y-axis of each subplot, making the subplot cleaner and more suitable for displaying the images without axis marking. So this code creates a figure with 4 subplots, arranging them in a row and display 4 images LL, LH, HL and HH along with the tiles. So these images can display in a grayscale without axis tick mark, and this type of visualization is commonly used in image processing and signal processing to display the result of the various images, transformation and analysis. The next code is fig.tight underscore layout. This line is called after the loop and subplot customization. The function is used to automatically adjust the position of subplots within the figure and so that they fit together nicely without overlapping. These can be especially useful when you have multiple subplots in a single figure. So as it ensures that they are well arranged and properly spaced, preventing elements from being cut off or underlaying with each other. And last line of the code is plt.show. So finally, the plt.show function is called the display the entire function is necessary to actually renders the display the figure including all the subplots after all the customizations and arrangement have been made. Without this line, the figure would not be visible to the user. In summary, these lines of code help enhance appearance and layout of the figure with subplots containing images. They remove axis tick mark to reduce clutter and ensures that the subplots are properly arranged and spaced with the tight underscore layout method, and then display the entire figure using plt.show method. So our final code for wavelet transform and its output is shown in the figure number 3. The Python is a versatile programming language that can be used on various platforms and operating system. So we can type this code in Python on the following platform: a local machine, Windows operating system. We can choose Python by downloading the Python platform from the official website www.python.org. So popular integrated development environment IDEs for Windows include VS Code, PyCharm and IDLE. There are some online Python editors also. If you do not want to install Python locally, you can use online Python editors and IDEs like Jupyter Notebook and Google Colabs and CodePen. We are implementing these code in Google Colab. The complete code and its output is given in the figure 3. Here we can see that the various approximation subsignals that shows the general trend of the pixel values, and these details subsignal shows the horizontal, vertical and diagonal details of the image. Now we will implement the code for wavelet based image compression. So for this we will take the figure number 4, which shows the sample code. I will explain each step in the detail. For this Python code which performs image compression using wavelet transformation. Here's an explanation of each part of the code is: the step 1, import all the library files. So type import pywt. It is Python wavelets library for wavelet transformation. Then second, import numpy as np. It is numpy for numerical operation. Third, import cv. This is OpenCV for image loading and saving. The matplotlib.pyplot as plt. It is for displaying the images. And then second, we have to create a function. The name of function is wavelet underscore compression. This function takes two arguments: image path, the path of input image, and the compression ratio, a value between 0 to 100. It is indicating the compression level. It loads the input image into the grayscale using OpenCV. Then the third step is specifies for the different subplot. So titles equal to approximation, comma, horizontal detail and vertical detail and diagonal detail. Now we will apply 2D discrete wavelet transformation to the input image using Bayer 1.3 wavelet. So we type coefficient COEFFS equal to pywt dot dwt to image comma BIOR 1.3. The DWT decomposes the image into the four equal part: approximation LL, horizontal detail LH, vertical detail HL and diagonal detail HH. Then extract the different coefficient LL, LH, HL and HH equal to coefficients. Now we sort the threshold approximation coefficient using LH based on the specific compression ratio. The threshold equal to np dot percentile. So np dot absll comma compression ratio. Here the LL is less than threshold equal to 0. Create a matplotlib figure to display the compressed image and its components in subplot. For this we type fig equal to plt.figure, figure size equal to 12 cross 3. Then iterate over the four coefficient components and display them in the separate subplots. This same line is already discussed in the previous section. For I, A enumerate LL, LH, HL and HH. Here AX equal to FIG dot add underscore subplot 1 comma 4 comma I plus 1. AX dot IM show A interpolation equal to nearest, CMap equal to PLT dot CM array. Then AX dot set the title method. Then AX dot set X tricks method. Then AX dot set Y tricks method. So all these codes create a figure with four subplots, arranges them in a row and display in the four images LL, LH, HL and HH along with the titles. So these images are displayed in a grayscale without axis tick marks. This type of visualization is commonly used in image processing signals. The processing to display the result of the various image transformation or analysis. Now, we show the compressed image and its component using matplotlib. So we use figure.tight_layout and plt.show. It will display the result. Then we can reconstruct the image from the compressed coefficient using inverse DWT. So now we write reconstructed underscore image equal to pywt dot iwt2 ll lh hl and hh comma by 1.3. That reconstructed image is written by the function. Then the define main function. These main functions has some parameters. First, the input image path. In this case, we have taken test1.jpeg, set it to compression ratio, that is a 90, and compressed image equal to wavelet underscore compress image input image path and compression ratio. Then image equal to cv2.imread compress the test1 file in JPG format and then compressed image. It specifies the input path, input image path and compression ratio. It calls the wavelet underscore compress function to perform the image compression and save the compressed image using OpenCV. For this, we type cv2.imread. The first parameter is compressed underscore test1.jpg, comma compressed underscore image. The code executes within the main function if the script is run as the main program. For that, we can call the main program using main method. The output of this code is shown in figure 5, which is implemented in Google Colab platform. It has a current working directory called content folder. So here we can upload our input text file, which is text1.jpg. is it display in the left pane area of the figure, and we can also view the size of this input figure test1.jpg file, that is 270.04K. After executing the code using click on the run icon or a play icon, the code will take few minutes and decompressed file will be generated in the current working directory. The name of output file is compressed test1.jpeg, which is shown in figure 6, and we can also see the three details subsignal show the horizontal, vertical and diagonal details of the images. At the bottom of the code, they are horizontal details, vertical details and horizontal details. Then, if we necessary, perform any additional post processing steps such as color conversion or a contrast adjustment on the decompressed images. In summary, implementing wavelets in Python can be a powerful tool for various signals processing and data analysis tasks. However, it is important to carefully consider and specific requirement of your application and the characteristics of your data to make effective use of wavelet analysis. Wavelet compression is a powerful technique to reducing the size of data while retaining essential information. It has been widely adopted in previous domains where efficient data storage or transmission is crucial, such as a digital media, scientific data analysis, and medical image. The key advantage of wavelet compression lies in its ability to capture both fine and coarse detail in data, offering a flexible approach for achieving the desired compression quality. Thank you for joining today's lecture on applying wavelet based image compression using Python, and looking forward to seeing you in the next video lecture or whenever you need to support. Have a great day. Goodbye.